NASA satellites in low Earth orbit rely on the near-Earth network to bring down 1,500 gigabytes of data per day. The NEN's 42 antennas, spread over 17 ground stations, provide direct-to-ground customer-based satellite data transference 24/7, 365. NEN antennas as large as 60 feet in diameter track rapidly moving satellites up to 1 million miles from Earth. The NEN can take 150 passes per day, supporting up to 40 missions.
What makes the near-Earth network best in class is our proficiency. We have a proficiency greater than 99.1% requirement, but we're typically at 99.8%.
Driven by customer demand, the NEN continuously develops and implements network improvements.
We're upgrading the NEN to a K-band network, which will enable us to support science missions with a higher data rate. We have a highly skilled, highly motivated, highly dedicated team that's willing to work late hours, whatever it takes to get the job done. The challenge is to manage a project and to stay on schedule and within budget.
Launches it around, assigns it to the antennas with a little bit of care and feeding from the people who are actually running the scheduling office and from the network, not the management office, but the NPAO, Program Activities Office for the NEN. And what they'll do is they'll put some rules together about when and where we're contacting the satellites and how we're going to get that data down. And then this is what type of contact it is. So we have a file on our server which says for the AIM spacecraft, for example, we're going to encode the data this way. It's right-hand circular polarized, all the different parameters that are through there, and we'll pull that file up using this schedule and then run through here. The top part of this is a graphical display to tell you when those contacts are going to come in and when they are, and which antenna it's going to be for here. And we do the same thing for the other sites that are using this automation.
Can we go see the 11-meter control room?
Sure, if you want. I'll give you a quick look here. Well, this is the easy one. It's got pretty pictures. Oh. Pretty pictures really are fun. But there's a couple things that we do here. One, I'll point out this, and you can get that same kind of display in your iPhone or your Android if you're doing amateur work, where it's going to show you where that spacecraft is going to come through. This little red line is the plot of where it's going to be. That's pretty low on the horizon. So the spacecraft, the antenna will actually line up on it and then track it as it goes through that path. Sometimes it goes directly overhead. A lot of times it's off at an angle, but it kind of shows you where it is. And as we're making that spacecraft contact, you'll see the little dot moving, which is the spacecraft, and that antenna is going to be tracking on that to see where it's going. You see a couple of other screens here, and these are, I just forgot the name for them, but spectrum analyzers. And the spectrum analyzers are what's going to tell us that we're actually receiving the data. Right now we just got noise. But when we lock onto a good strong signal, we're going to see that signal come through, and different spacecraft have different characteristics of what their spectrum looks like. So we'll see the side lobes and then the main lobe, and then it'll also show us what the power is of that, and we're tracking and gathering all that information because it provides information either to the flight dynamics facility for them to help calculate the orbit, or to be able to look at the spacecraft performance and see how it's doing. So they can see if the antenna is doing well as pull the telemetry down from that antenna, which is saying I'm hot or I'm cold, or my battery's not charging, or my solar panels aren't working correctly, or my camera doesn't work. You know, different things, and it'll tell us a lot about that spacecraft and what it's operating. And then of course the setup configurations here. Normally when we pull that script file down, it's going to pre-populate all of this data for us, so we get a successful contact every time. And like Scott said, there used to be a team of people that were, as soon as the one pass was done, they're pulling up the manual sheet and they're running in the back and they're setting up the machine and all the different analyzers to track on the next one. Well, now, happens all here. These guys still know how to do that, but they only need to do that in case there's a problem. So the automation actually works very well, but we do keep it back up, but it's become a very, very small crew. And very efficient. And instead of being at each site, we're doing this remotely. We still have technicians at those remote sites to run out there and replace a piece of equipment if it fails, but a lot of this has become very, very automated. Communications key. That used to be the old control center in there. They moved it out there to provide a little bit more space, but you can see all different kinds of things. These are what's called a programmable telemetry processor. Basically a very specialized, fancy computer that takes input signals, non-traditional, the old TTL versus our Ethernet, although that's probably going to change in the next couple of years. But what they'll do is they'll actually process telemetry and provide it out to the customers. We also use some things called Zodiac transceivers, which is actually the radio, which can do some processing, and then it passes some processing over to these. So they'll actually generate the signal going up to the spacecraft, receive that signal coming down, translate it from a radio signal into a data signal, and then that data signal gets either pushed out through some of these massive computers that are here, where they're basically big old storage devices. So is anybody an IT background? Wouldn't you like a hard drive like that?
Well, if you're getting rid of one,
it's actually got a whole bunch of these little 2 to 4 gigabyte hard drives inside of it, and there's a whole bunch of them. There's a couple of different ones here. So we have a lot of storage, but we only store for maybe 2 days at the most, where we pass that data back. We actually will record a lot of data, and we have what's also called a wideband recorder, where not just the signal, here we're recording the signal, the wideband records everything. And then if there's a problem where they don't get the data correctly, we can either replay it or go back to the wideband and pull the whole thing back through this whole system again and retranslate that entire signal and then provide it back out to the customer, because we don't want them to lose their data. And they really don't want to lose their data. They're very concerned about getting accurate science data so that they can see what's going on, because they are looking at this both in layers, depending upon what the science experiment is, but also in time. Because over time is where they see the changes. And a couple of ones that you hear about is sea ice. This morning they were talking on the radio about the ice coverage on one of the Great Lakes. This year it's about 90–95%, whereas in past years it was 50% or something else. This year has turned out to be apparently a little bit colder than what it had been. They monitored the ice pack in the Arctic, and if you've ever watched the guys catching our crabs, the crab fishermen, they worry about that ice pack coming down through the Bering Sea. Well, we've monitored that also, because it's a general indication of what's happening to our Earth. Is it heating up or is it cooling down? And that's what we're trying to figure out. And a lot of really smart scientists have been working on this to try and solve this puzzle to figure out what's going on. Radio amateurs are doing that too, by the way. Everything revolves around the sun, including us. And the sun and the sunspot cycles really affect a lot of the things that happen. They're an indicator of what the sun is doing. And what we're discovering is that over time the sun changes and it has cycles. In some cases, you know, you heard about the 11-year sunspot cycle. It averages about 10.6 years, but as part of a multi-100-year cycle and maybe a multi-thousand-year cycle on the sun, we don't know yet. When we're around after another 10,000 years, we can look at our data and see how it is. Well, maybe we won't be there in 10,000 years, but we know that things are happening, and we're still trying to understand what they are and do those kind of things. The world is changing.
Good.
Well, thank you very much for coming out. It's our pleasure to have you.
Thank you very much.
Enjoy your visit.
Thank you very much.
Our pleasure.